Okay, dear calculus students, today I'm going to show you guys how to do some calculus with this roll of toilet paper. So the next time when you see the roll of toilet paper, you know what to do with it. Anyway, the goal is to find the volume of the toilet paper, and we want some actual measurements. Of course, I have the ruler. I can take some measurements for the height and also the big radius and also the radius of the middle part, right? I put them down over there already. So let's go ahead and just get to work. First off, we know that we can just use the volume of the cylinder to finish this question, but let's not do that. To use calculus, two major ways to find this kind of thing, which is actually just a solid of revolution. The first way is called the disk and also the washer method. Whenever there's a part that's missing in the middle, just like this, that's the washer method. A disk is just a very thin cylinder. It's like a radio plate. It's like a CD, but nobody listens to actual CD nowadays, so yeah. But anyway though, it's just a really thin cylinder. Well, the cross section here is a circle, so we need to know the radius. And then right here, usually people put H for the height, but this is so thin, so I'm just going to put down thickness. And for the volume of a disk, it's just pretty much the volume of a cylinder. We need to know the area of the cross section, which is just a circle, and that will give us pi r squared, and then we have to multiply by this, which is the thickness. And the idea of doing the disk method is just that we are going to cut this into infinitely many small disks, and then we are going to find the volume of each of them, and then at the end we are going to add them up by using integration. And when we have a washer, it's really just when we have a hole in the middle like this is a washer, right? It's the tool. Yeah. So anyway though, let's break this down. First, this right here, we can look at this as a rotation of certain region, and of course we will just draw a picture first. So let's say this is the outer part. So let's go ahead and put this down, and we also need the x-axis and the y-axis so that we can actually do the math for this. Okay, so the big radius from here to here is 5.5. So that means our x value here will end at 5.5. And then the height right here is 11.5. So I will just say this right here is 11.5. All right. And that's pretty much all we need for this picture. And then we will have to minus the middle part. So for the middle part, I will put this down right here. It's just a smaller cylinder, right? And then let's still put down the x-axis and also the y-axis. And from here to here, the radius for the smaller one is just 2. So I will just put down 2 right here. And then this right here is still 11.5. And of course, I'm ignoring all the units because at the end we'll put on the units, because all the units are the same right now anyway, so there's nothing tricky. So how does this work? Well, to use the disk method, what we want to do is look at this and then just cut this into smaller disks. So usually we like to just draw a picture like this, and this is the horizontal slice, so that you can kind of match that cylinder, right, when you pile this up. And don't worry, later on I'm going to give you guys like a typical calculus question, because I know this right here is like, why don't we just use the big formula, right? I want to use this because later on I can talk about the shelf method. So let's just continue watch this. Okay, once I draw the red disk right here, what I will do next is I will label the radius. But you see, the radius is from here to here, which is the horizontal distance. I will put down x. Right? So the radius is the x right here. And then I will try to figure out the thickness, which is from here to here. But that's just a small change in the y values. So in calculus notation, I'm going to label that as dy. And with that being said, let me tell you, the volume of the red disk is just pi times the radius, which is x, and then square that, and then times the thickness, which is dy. That will do it. Okay? But this is not good enough, because this is just one disk. We want the whole thing. So we have to add out all the volumes for the disks. And to do so, we use the super version for adding in calculus, and that's the integral. And when we are having dy, usually I like to tell my students that this is in the y world. we will have to look at the y values from the starting to the end. This right here is on the bottom, which is at y equals 0, and then we finish at y equals 11.5. So we will go from 0 to 11.5. So that would be the first integral that we have. But of course, I know x is not inviting the y world. Don't worry, I'm going to fix that later. Let's also set this up right here. We are going to subtract integral. And for this right here, do the same thing real quick. You know, draw the small disk like this. Again, horizontal distance is dx, and then the thickness is dy. Very nice. So pi x squared dy, and this time we still integrate this from 0 to 11.5. Perfect. Now, x is not inviting the y world, so that's no good. We will have to look back to here and then look at the equation for x. Notice on the side here, this is what we have. That's the x. And in fact, it's just a vertical line. And in fact, x is always equal to 5.5. So we can actually just put that right there. Similarly, right here, the x is just always equal to 2. It does not change throughout the process. Later on, when we are doing like a curvy shape, you have to be really careful with that. But for now, we can just say this is the integral going from 0 to 11.5. Pi is still pi, and then x for this is 5.5, and then we square that dy, and then we minus the integral going from 0 to 11.5, and then we have the pi, and then the x right here is 2, and we square that, and then we have dy. And that will do it. Just compute this, and then we'll be done. And usually when we go over these kind of questions in my class, I would just ask the students to set it up and then use a calculator to compute, because the setup for this kind of things is much more important. And of course, sometimes if you set up the integrals wrong, there's no reason for you to do the wrong integral, right? And that's not good. So set it up and use a calculator to do it, and I'll tell you the answer is approximately 948.37, and this right here is the time that I will put on the unit, which is centimeters cube. So this is the volume of the toilet paper. Next time, you know. All right, this is just one way to find the volume when we are doing the solid of revolution. The other way, and this is why I have the toilet paper, all right? So the other way is called the shell method. So what's a shell method? Let me demonstrate. Earlier, of course, you could have just used the volume of a cylinder, the outside minus the inside, done deal. That's pretty much all we did. But let's look at it this way. Toilet paper is perfect because you can take the toilet paper from here to here and then just unroll it one revolution, right? And then you can just tear it apart. So let's say this is one revolution. And imagine if you just keep doing this, you go around again. Okay, that's good. If you continue doing it, I'm not going to do it anymore because I want to use it later on, right? And then you can actually pile this up. Once you pile this up, you can calculate the volume for this. Same thing, huh? Of course, it will give you the same answer because we are talking about the same toilet paper. And now let's analyze this. When we unwrap each revolution, right? This is technically one revolution. I think I just didn't do a good job, but just imagine this is one revolution. Once we unwrap it, what kind of shape are we getting? It's a rectangle, huh? So we are actually going to look at the volume of this sheet of toilet paper, aka a shell. Does this have volume? Yes, it does. Well, we need to first know the length. And where did we get the length? Well, earlier we unwrapped one revolution, so that's the circumference of the circle, huh? Of the cross section here. So the formula for that is 2 pi r circumference. And then right here, this is still the height, right? So we have the dimension for the rectangle now, but technically this right here has a volume because it has a thickness right here as well. So it's like the height. So for the thickness, I will just really have to do this. Yeah, it's not this thick, okay? I know it's not this thick of the toilet paper because it just does not work in real life. But I just have to put this down so that we can all see it. And then right here, we have the thickness, just like that idea earlier. Okay, that's the thickness. So once again, we'll be using the same idea. We will first have to find the volume of a shell, but now we can see that based on this picture, the volume of each shell is just nicely equal to the volume of this thing, right? It's a rectangular prism, technically speaking, but it's very thin. Anyway, we just need to multiply this and that, which we have 2 pi r h, and then we also multiply by the thickness. You know why I haven't erased this yet? Well, earlier, for the thickness of the disk method, we had what? dy, right? So remember this right here is either dy or dx, depending on how we do the slice. Well, for the thickness right here, it's also going to be dy or dx. And the thing is, if we use dy for the disk method, then if we do the same question for the shell method, it will be dx. So let me just purposely write down dx right here first. And if we have to use dx in this situation, then the same question, when we use the shell method, it will be dy. So that might be pretty good sometimes, because sometimes when we are solving like a function equation, maybe we cannot isolate the x or isolate the y, then we will have to change. But anyway though, this is the answer that we have, and now let's look at how we can use the shell method to find the volume of the toilet paper. And for that, let's just go ahead, use that picture right over there. Here is the deal. I am still going to write this down, I'll just redraw it, but this time though, I will have to put down the x and also the y-axis. Sorry, horrible picture. Let me do it again. So here we have this. I know it's not any better, but yeah, sorry. All right, we have the outer part, and then of course we also have the inside part. Okay, and that's of course that's the x-axis, and here is the y-axis, and this is how you are going to draw the shell. All right. What you have to do is just imagine that you are going to take out a revolution of the toilet paper. So to do so, I'm just going to make a vertical cut right here like this. And then I'm just going to go around. So this is that sheet of toilet paper that we are about to take out. So that's the idea. Now, we know that this right here, when we unwrap the toilet paper, we will have 2 pi r. So what's the r though? Well, it will be going from here to here. And again, that will be the horizontal distance, which is x. How about the height? Well, that will be the vertical distance, which is the y. And there's one more thing that we have to label. How about the thickness? Look at the thickness that we have here. It's just a small change in x. So that will be dx. Alright? So you see radius, height, and also the thickness on this picture. Now, if we take this and then wrap it, we will get this. And the volume for that is just nicely equal to 2 pi r, which is the x, and then multiply by the y, and then multiply by the thickness, dx. So this right here is just the volume of this particular shell. But this is not enough. We want the whole thing, right? We are going to add up everything by using integration. Now, check this out. We are in the x world now. So we have to look at the x values going from what to what. What do you guys think? Well, look at this right here. This is like the starting of like the very last row of the toilet paper, right? And that's at x value 2. And then this right here is at x value 5.5, right? Because from here to here, the radius is 2. From here to here, the radius is 5. So therefore, we are going to integrate this from 2 to 5.5. Now, can we integrate this already? No. Why not? Well, y is not inviting in the x world. The x is okay. Leave it. Okay? So what do we do though? Well, have a look. This right here is the y. And the good thing is that y is always 11.5. It doesn't matter where you unwrap the toilet paper, like the very inside or very outside. The side right here, which is the height, is always 11.5. It's a constant. So we just have to put 11.5 right here, and we will get the integral going from 2 to 5.5, and then we just have 2 pi, you keep the x, and then the y is 11.5 dx. Okay, dx. And then we can just go ahead and integrate this, and again you can just do it on your calculator. 948.37, I guarantee you, centimeter cube. That's it. All right. So now, hopefully this right here makes everything clear in terms of what the shell method is and also how we use the disk method. In my opinion, the disk method is more natural for us to understand when we first learn these kind of things. The shell method is kind of like what exactly is going on. And in fact, I will have to give a shout out to my former AP Calculus teacher because I didn't come up with the toilet paper method myself. I learned it from my AP Calculus teacher, Mr. Schneider, Mr. Thomas Schneider. If somehow this video gets to you, then I just want you to know that I still remember you. Thank you so much for the teaching. That was so many years ago. I don't want to tell you guys how many years ago because I don't want to tell you guys my age, but yeah. All right, let's take a look at another example. And for this example, it's a typical calculus example that you guys should know. So let's look at a typical graph. Yes, y is equal to x squared. Let's not do anything crazy. Just look at a parabola, all right? So it's a nice, innocent, friendly parabola. And let's just go ahead and say, we first need to have a region. Let's go from 0 to 2. Let's say 0 to 2 is right here. So this is the region. And then when we have a region, we can either rotate it about the x-axis or about the y-axis. But because earlier we did it with the y-axis, let's keep it with the same one. So I'm going to rotate this about the y-axis. And if you guys want to see more examples like this, I have a lot of videos on this kind of things already. Check them out. Links will be in the description for your convenience. How do we draw the picture for the solid of revolution though? I will show you. Do a mirror image on the side like this. And on the top, just go ahead and draw two ovals. One oval right here, and on the bottom, draw another oval, like that. That's pretty much it. Let's use the disk method for this first. Technically, they will call this the washer method because, again, the middle part is missing, but you know, it's just one disk method minus the other one. So let's look at the outside first, which is just a very nice cylinder, like what we did earlier. So that's what we have. And then, of course, let's also stick out the y-axis. And then let's subtract the inner part, which is like a bowl. So it will look like this now. All right, and again, let's put down the x-axis and then the y-axis. Now, for this right here, again, just like what I showed you guys earlier, we will just make a horizontal cut. Usually when you do this, I think it helps, especially when we first do this kind of questions. Right, we make horizontal cuts. And then it's all about labeling. We want the radius is from here to here, which is just the horizontal distance, and that will be x. Look at from here to here. It's just a small change in the y values. So that will be denoted by dy. And what's the formula for the volume of the cylinder? Pi r square h. Okay? So the volume of this red disk is just pi r is x, but in this case, do we know x is equal to what? The x is in fact always equal to 2, because it was right here, right? The outer piece is always right here. So x is equal to 2, we can just put a 2 inside, and then we square that, and then we have dy. That's it. X is always equal to 2 and then dy. So that will be good. And then we will just have to integrate this from 0 to what? Beginning to the end. The y ends at 4. Because when x is 2, 2 squared will give us 4. I didn't write that down, but we will be able to compute that if the question didn't give you that y value. So we go from 0 to 4, so that will be the first part. Alright, so that will be it for that, and then we will just have to minus. And for this volume, go ahead and do the same thing. Draw a disk like this. We need to know the radius, which is denoted by x, and then right here is dy. And now you might be looking at this and then say, this is so weird. This is not a disk because there's like a missing part. But technically it is. When you slice this very, very thin, it's a disk. Okay? So we still do the same thing. We still have pi and then r square, and then we have the dy. But now, what is x? Can we just put x down right here? No, because x is not infinity in the y world. So what do? And notice that right here, x changes. So it's not just a constant. Okay? The radius from here to here is this much, and then once you go higher, it gets longer. So it changes. Don't worry. Look back to the equation now. We know y is equal to x squared. Just take the positive square root on both sides. This means x equals square root of y. Therefore, we are just going to enter square root of y right here. And this right here will be the volume for this blue disk. Not Blu-ray, blue disk. Oh, I know it's not funny. But anyway though. And then we're going to just integrate this going from 0 to 4 as well. And I will tell you this right here will be the integral that will compute this volume of revolution for you guys. I'm not going to do it. You guys do it and let me know what the answer is down below. But I will also do the shell method for this particular volume for you guys as well. And then you guys can check if they give you the same answer or not. So now, by the shell method, I'm just going to draw the picture right here again. So it will look like this, right? So on the left hand side, so on the right hand side will look like this. And then I'm just going to do a mirror image like this. And then we have that, right? So this is like the solid part. And then we have this, and that's putting the x-axis and also the y-axis. This is the horrible picture. I'm sorry. Something like this. This is the x-axis, and this is the y-axis. Okay. All right. So now, how do we draw a shell? You do this, right? Vertical cut like this, and then you pretty much just go around like this. It's like you want to wrap it around with a sheet of toilet paper. Well, not a sheet, like one revolution of toilet paper. So you do this, and on the top is an oval, right? So make sure that you know there's a thickness of this thing. So that would be a shell. All right, labeling time. Radius is x. The height is y, and then the thickness of this is dx, because it's a small change in the x values. And again, if we use dy for the disk method, then we'll use dx to do the same question if we switch to the shell method. And then by looking at this, we know that the volume of the red shell is 2 pi r, which is the circumference. So let's put that down, 2 pi r. And I'm just going to write it down as x first, all right? And then multiply by the height, and then multiply by dx this time. All right, and then we are going to integrate this. By the way, I shall say this is the volume. So yeah, and then we are going to integrate this. We are in the x world, so x goes from where to where? You can look here, right? X goes from 0 to 2. So it goes from 0 to 2. So when you do the shell method, yeah, if there's missing part in the middle, sometimes you don't have to subtract because this right here takes care of that. Now, we just have to pay attention to what matters, what doesn't. The x doesn't matter, it can stay in the x world, but for the y, no good. So what do? Well, x is just okay, but y is what? We can go back here, y is just nicely equal to x squared. So we're just going to put down x squared right here, and that will do it. All right, so I will just perhaps put this down right here, y is equal to x squared. And I'm just going to write this down, integral going from 0 to 2, 2 pi x, and then x squared, and then dx. And I am going to leave this to you guys. you guys can multiply this out and then use the reverse power rule, work that out, or maybe just use a calculator to finish all that. So hopefully this video helps you to understand how to do the dishwasher method and also the shell method. So yeah, let me know if you guys have any questions. Just drop them down below or check out my other videos for more examples like this. This is actually one of my favorite part of Calculus 1. Yeah, that's it.